Hello everyone. So recall in our last video that we went over some definitions of series and sequences, what a convergent and a divergent series is, and we also talked about our first test which we can use to assess whether a series, in this case diverges, which is the test for divergence. It's a pretty simple test. All it involved was taking a limit. So this is yet another very simple test that we can use to test if a specific type of series converges or diverges, and these are called p-series. And you're actually going to notice that the things we talk about in this video are very similar to a subject which we talked about just a few units ago, back when we were doing integration. So let's take a particular series which is called the harmonic series, which is 1 over n. All right, so if we take that as an infinite series, well, we're just going to get, if we start at n equals 1 and go to infinity, we're just going to get 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, and it's just going to keep on going, okay? So again, if we do our test for divergence with this series, if we take the limit of 1 over n as n goes to infinity, well, we're going to get that that's equal to 0. So remember, that basically just means that we don't know for sure that this series is going to converge or diverge. Let's look a little bit more in depth at this series. So look at these terms right here. If we look at just what the sum is going to be, and look at this graph that I put down here. Notice this is the graph of 1 over x. I've basically just taken the sequence 1 over n and replaced the n with an x. This series started from n equals 1 and went to infinity. So I'm going to start with x equals 1 and then go out to x equals infinity. And what do you notice? Well, you notice that this series, 1 plus a half plus a third, is exactly the same as taking a left Riemann sum of the function 1 over x. Remember, we're just converting the function 1 over n to 1 over x. From x equals 1 to infinity, in this case we have a step size of 1 every single time. So all of these rectangles, the area of these rectangles match up with what we get in our particular series. So this is really cool because it basically tells us something very interesting about the relationship between integrals and the relationship between series. Now remember, I said this when we discussed Riemann sums just when we were first talking about integration. But if we do a Riemann sum, basically an integral is just a Riemann sum taken out to an infinite amount of terms when the base of our rectangles gets infinitely small. So basically when we've been doing Riemann sums, we've kind of been doing something similar to infinite series the entire time. And when we actually evaluate an integral, we are actually evaluating an infinite series. So this brings everything right back around to why it's important to assess convergence or divergence of series, is because if we have a convergent series, that if we're applying that to a Riemann sum to evaluate an integral, that means we can actually evaluate that particular integral. Okay, so what we have is that the area under this curve, or this left Riemann sum, is going to be an approximation for this integral right here. Now, it's going to be an approximation. It's not going to tell us the exact same thing, but what unique thing arises out of this? Well, remember that if we have an integral like this one right here, that's called an improper integral, and we actually had this cool relation, this cool rule that dealt with a very specific type of improper integrals. And that was that if we had an improper integral of this form, the integral from 1 to infinity of 1 over x to the p dx, we knew that if that value of p was greater than 1, then that integral actually had a value, and in this case it's convergent, or if p was less than or equal to 1, then that integral would be divergent. Well, the same holds true for infinite series. If we're given this series, and notice in this case I'm saying we'll start at some value capital N. That value could be capital N equals 1, it could be capital N equals 2, 3, it doesn't matter. As long as it's not equal to 0, that's the one thing that we don't want to have. So anyway, basically if we have a series that looks like this, a series from something to infinity, an infinite series that looks like 1 over n to the p, we have the exact same rule that this series will converge if that value of p is greater than 1, and it diverges if that value of p is less than or equal to 1. So now let's go back at what we've talked about. In the last video we saw the test for divergence. So if we're ever given a series, we can immediately run that test for divergence to quickly see if the series diverges so we don't have to waste our time doing any kind of convergence tests. And if it's not that case, if the series happens to be in this particular form, then we can just look at it as a p-series and look at that exponent in the bottom. Now remember, the one that we looked at up above was the sum of 1 over n. This is called the harmonic series, and it's actually a divergent series. And the harmonic series is something that we use a lot in a particular type of convergence test called the direct comparison test, which we'll discuss briefly in this unit, but we're not really going to spend a whole lot of time on it. But anyway, it's a very easy test, very straightforward, just a quick way you can tell if a series converges or diverges. But it only works for ones that meet this particular form. Also, remember that rule that we had about constants. Like, for example, if we have the sum of, let's say, 2 over n or something like that, we'll realize that we can just write that as 2 times the sum of 1 over n. And now that we know that 1 over n is a p-series with p is equal to 1, which means it's divergent, that means this series would be divergent too. So with this knowledge of p-series, now we can kind of, whenever we're given an infinite series to test whether it converges or diverges, one of the first things we can check is, does it match the form of this p-series? And if it does, it's a very quick, like 1 second analysis to determine whether that series converges or diverges. So there we go. You've learned your first test for convergence or divergence. In the next video, we're going to talk about a category of series a little bit more in depth, but again, one that is a very important one when it comes to the types of series that we are going to encounter in this class. So I'll see you there.